All right, can you hear me? That sounds like the mic's on. All right, cool. Thank you, guys. I was a little worried. The 3:40 slot seems like the going to sleep slot, but maybe the popcorn is keeping you up. So, I just want to give you guys heard a lot about Kubernetes. We're really excited with the partnership with CoreOS. Some of the announcements that have gone out today, but I just wanted to give you a broader sense. Many of you may have played with it already. I'm seeing some stickers on laptops. That's pretty cool. But I just want to kind of catch everybody up with what we are trying to do with this project. All right. So this is my way of starting out. This is the image that I have that's starting out. And the fundamental notion behind this image is, well, what makes a semi-truck harder to drive than a car? And one of the main problems with a semi-truck is actually that it's actually a two-dimensional problem. It has this coupling here, and anybody who's tried to back up a trailer or back up a semi-truck knows that this coupling between the tractor and the trailer makes it a much harder problem than if each one of those were individual cars that had no coupling between them. And really, at a fundamental level, that's what Kubernetes is about. It's about decoupling all of these different pieces from being highly connected, interdependent problems where you make one change over here and you don't see the ripple that it causes until you're paged in the middle of the night, into a series of totally independent, decoupled problems that you can actually hand out to different people with different kinds of expertise that they can solve individually, and oftentimes without the other people knowing that there was even a problem, right? So many times when I'm carrying pager, people other than I wake up in the middle of the night and fix problems with the system that help my software keep running, and I don't even know that they've been awoken, and that's a really amazing thing. And that's because we've achieved this sort of decoupled infrastructure. All right, so to give you a more detailed perspective about this and to sort of contextualize Kubernetes in some of the things we think about, I want to give what I think is a picture of the sort of the ops stack that exists. I was going to start, and when my slides were longer, I had a slide here that had Samuel Jackson saying, "Say DevOps again, I dare you." But I actually don't think that DevOps, which is sort of a dirty word, is actually really that much of a dirty word. I think they just they got the idea right, but the implementation wrong. I think that what they really meant when they said DevOps was they really meant application ops, what we would call application ops. And it's totally appropriate for a developer to do operations for the application that they built. In fact, many sysadmins who I've met, I wouldn't want them going anywhere near my application, just like they don't want me going anywhere near the kernel, right? And so one of the things we want to be able to decouple is all sorts of the operational expertise. Developers do operations for their application. Cluster admins do operations for clustering software like Kubernetes. Kernel and operating system operators do ops for the operating system in the kernel, and that's where something like CoreOS and their updates come in. And of course, anyone who's using an IaaS system has actually already outsourced their hardware operations to the public cloud provider. And so this really means that this specialization means you get to focus on the thing you know and the thing you understand. No infrastructure as a service provider worries at all about what somebody is running on top of that x86 as a service. And I think this is the right way to go about things. And so Kubernetes is really about trying to provide a cluster, a decoupling between you and the hardware ops and the kernel ops below you, and the application ops that you're providing on top. And so what this also means, if my slides move over, there we go. What this also means, and this is sort of a different picture of the same thing, is that your application containers view the world essentially as this sea of compute. And Kubernetes means it takes any machine that you have available to you, they're entirely homogeneous. Every single machine that you create in your fleet looks and feels exactly the same. And they're indistinguishable, so that if one of them dies, it doesn't really matter. All your application sees is there's slightly less compute available in the pool. That's a really powerful abstraction. It means that I don't have to worry about what's going on in the operating system. I don't have to ask someone to go and install a particular version of an operating system or a particular version of a library. And I don't have to worry that somebody else is asking for an upgrade to a library that I also depend on. This decoupling of the application from the lower level compute on which it runs really enables both the application developers and the people who run the machines to live easier, happier, more decoupled lives. All right, so the next thing I wanted to talk about then is what does this Kubernetes API actually look like? What does it actually provide you as an application developer or an apps ops person as the surface that you can interact with and build your application on top of? So the first and fundamental, I guess arrow keys are not working, I will click. So I want to give you first an overview of the Kubernetes architecture. And it all sort of starts with the API server. That's the thing that makes the API available to you. That's the interface through which you interact, either via kube control, which is our command line client, or Ajax API over, Ajax from a web API, or any other client. It's an HTTP RESTful API. So if you want to, and we actually have Swagger support now. So if you want to generate clients and use Java or Python or anything else, you can use those libraries as well. Now the API server itself and all of the objects in the API server are actually backed out to etcd. That means the API server is stateless. It means you can do upgrades and you can replicate it and things like that. And etcd is actually providing the storage behind the scenes. That's really powerful. Now we also sort of take the philosophy of small binaries that are focused. And so to that end, we also run two other binaries in the sort of master side of the house, and that's the scheduler and the controller manager. The scheduler is responsible for, well, scheduling containers out or pods out onto machines. The controller manager is responsible for doing health maintenance. So something that's very important for the Kubernetes architecture as a whole, and then we'll talk about in a little bit, is this notion of reconciliation and self-healing, right? A lot of systems that do deployment and do orchestration, they're great at getting your software deployed. But once it's deployed, they don't do so much to keep it alive, right? Kubernetes is really intended to be an online system, a control system that is responsible not just for creating the world, but actually maintaining and healing the world, so that again, when something goes wrong in the middle of the night, Kubernetes can come along and actually fix it, and you never even get paged. And that's a really powerful thing for developers and administrators as well. And then on each machine, we have the kubelet, which is a small daemon that's responsible for managing the individual controllers themselves, as well as the service proxy, which is essentially there to provide load balancing and separation of the conception, we'll see this when we talk about services, but this conceptual idea of what a front end is or what a back end is from the actual implementation of the containers that are providing that service. All right, so I want to deep dive a little bit more into pods. Pods are sort of the atomic unit of a Kubernetes cluster. And really what they are is three things. They're a collection of one or more containers that work well together. They're a set of volumes that are data volumes, and the important thing here is that the lifespan of the data volume is independent of the lifespan of the containers. So there were some questions on the panel earlier about persistence and how we view state within Kubernetes and with containers in general, and I'd say we really want those lifespans to be decoupled, right? Anything that's in the container itself is transient. Anything that you want to be persisted probably needs to be network attached storage. Sometimes you want just scratch space, but you want it to live longer than a particular container because you're using it as a local cache, and if that container happens to crash and restart, well, it's really nice that the cached data is still there. And then finally, there's all sorts of namespaces that all of these containers share, from things like the network namespace to the IPC namespace, and essentially any namespace that you can imagine that is available for us to group together is shared amongst all of the containers that are within a pod. All right, so that sort of skip through those bits. And then the final part of a pod is that they have labels. And in fact, every object inside of Kubernetes has labels. These labels are just key value pairs, and they're really useful for organizing your things. One of the things we learned very early on inside of Google is that actually hierarchical representations of things inevitably fall down. You can make up a great representation that's perfectly aligned to your view of the world as a developer, and then the business guy will come along and say, no, that doesn't match up to billing at all, right? Your view of an application stack doesn't match up at all to the way that we bill for it. And so what we've learned from that is that actually we need to have the ability to have many different kinds of dynamic sets and allow people to sort of slice and query across the state of running things to provide the perspective that makes the most sense for them. And we'll talk about labels in depth in a little bit as well. All right, so I wanted to give some examples of pods, because this is one of the things that I think comes up. And people say, oh, great, a pod, multiple containers that work together. I understand that. That's like WordPress and a database. And I have to say, well, you could do that. But really, I think that the fundamental thing that you want to understand about a pod is that it's the atomic unit of scheduling. It's the thing where it doesn't make any sense for those two containers to land on different machines. And so the example of this that I like to give is you can have an Nginx web server. It's just sitting there serving data files off of a shared volume. And you can have a Git synchronizer. And the Git synchronizer's job is basically just to sit on a particular tag in a Git repo or a particular branch in a Git repo, and just keep the file system in sync with that particular tag or that particular branch. Two relatively simple tasks, serving web pages, synchronizing Git. You might say, well, why don't you just put them in the same container? And there's a lot of discussion about multiple processes and things like that. But the most fundamental argument I can put forward for separating them out is really separation of concerns. Because by putting them into separate containers and creating the Git synchronizer as one sort of micro container that I can use in a composable fashion, I can actually swap out Nginx, and I can replace it with Node.js, or I can replace it with Tomcat, and the Git synchronizer stays the same. So I really profoundly believe that containers offer us an opportunity, very much like object-oriented programming offered us, to build these composable, modular, reusable building blocks that's going to make it easier, and share them as well, and it's going to make it easier for us all to build distributed systems. I write Git synchronization once, and every single application that needs Git synchronized to the file system just reuses that. All of the best practices, all of the learning from all of the bugs and everything else go into my Git synchronization container. It's an independent, reusable component. And that's really what motivates pods in large part, is that you want to be able to have those things land on exactly the same machine in an atomic manner. It doesn't make any sense for my Git synchronizer to land on one machine and my web server to land on another. Now, volumes aren't the only thing that pods share. They also share a network namespace. So this means that my web application and a proxy, like a sharding proxy like twem proxy for Redis, can be connected together via localhost. This makes configuration much, much, much simpler, and has the nice side benefit that when I'm working on my web application, maybe I don't even have the proxy in the middle and I just run Redis locally on my machine. In both cases, localhost just works. So different containers within a pod can all see each other on localhost because they share the same network namespace without any kind of configuration. And then finally, because they also share other kinds of resources, you can have things like shared memory. Two different processes. A search index, which is a user-facing process, needs to be very high quality of service. And a shard loader, which is a background data processing process that really can sneak in sort of whenever, can communicate with each other through shared memory. You keep them in separate containers, again, because you want to have very different quality of service, very different CPU profiles for these two different containers because of their different purposes. And again, you can version them separately. You can even reuse them potentially. And again, this separation of concerns, decoupling of things makes management of the whole system easier. All right, so that's essentially all I wanted to talk to you about pods. Move on to the another aspect of Kubernetes, which is labels. So once you have these pods, you can start putting labels on them. So you can see here labels like front end or production or B. Burns, the user who created them, testing. All of these sorts of things become labels that are assigned, key value pairs that are assigned to these objects. And really you can use whatever arbitrary key value pairs you want. And what you can do then is you can issue queries against these labels. So you can say something like, I want stage to be production. And that selects out front end production, back end production, 2 back-end production pods and 1 front-end production pod. Or I can say, I want the stage to be production and the role to be back-end. And now the front-end has disappeared from this query in this dynamic set that I've created. And now I just have my production back-ends. Likewise, I could select on my name, my username, and I could see everything that I've created, regardless of its role, whether it's in production or staging or testing. I can see everything that I've created. So labels provide you with a really powerful, really flexible way to slice across the series of pods that you have deployed into your infrastructure. And they really form the basis of the next 2 API objects that we're going to be talking about. All right, I want to take a brief step back and talk a little bit about reconciliation. I have a robotics background. That's sort of where I came from long before, way, way, way back in the days when I was doing graduate school and not being at Google. And so I think that my sort of learning around control sort of influenced a lot of what we did in the days of developing the reconciliation loops that you see in Kubernetes. And the basic idea behind the reconciliation loops is that you have 2 things in the world. On the left here, you have your desired state, the statement about, the declarative statement about what you want the world to look like. On the right-hand side over here, you say you have the actual state. Maybe you've asked for 3 things to be running and only 2 are running. So you have desired state on one hand, actual state on the other hand, and the reconciliation loop's job is to take desired state, difference it from current state, and take action to try and drive current state towards desired state. Now, the simplest example of a reconciliation loop that you might run across is the thermostat that's on the wall of this room somewhere. And its job is to basically take the desired state, the temperature that it's set at, the current state, the observation of the current temperature, and take action, either heating or cooling the room, to drive the current state towards the desired state. So this is the reconciliation pattern, and it recurs throughout all of the sort of higher level primitives that exist inside of Kubernetes. So to just give a couple examples of this, you may say something like, I want to create pods. Well, when you create a pod, the scheduler actually goes to a machine and says, your desired state is that you're running these 2 pods. And that is in fact all that the scheduler says. And now the kubelet that's running on that pod is an example of this reconciliation loop. And so it has a desired state, I'm running pods foo and bar, and it has a current state, the currently running pod is foo. And so the action that it takes in that context is to create pod bar, right? That's the action that it takes. All right, similarly, just like the action of creation, health checking is actually exactly the same. Let's suppose that our pod has failed for some reason. It's not because it didn't ever exist, it's because it was there and it's now failed. Well, again, the kubelet that's running on the individual machine takes a look at the pods that are supposed to be running, and it sees my desired state is foo and bar, my current state is foo, and I better create, skipped ahead, I better create bar again. And this is really powerful because what we've seen now is that create and health check are using exactly the same logic. So that's one piece of logic that we had to write, one piece of logic that we had to unit test and debug and integration test and all of these things. It's not a big giant state machine. No offense to the big giant state machine that was up there for the Postgres replication. But I really prefer tight, small loops with desired state and expected state because they don't have any expectations about where they are. They simply observe the world, look at where the world is supposed to be, and they try and take a step towards the way the world ought to be. Now let's take a look at deletion. Well, here in deletion, my desired state is now that I'm only running pod foo. My current state is that I'm running pods foo and bar. Well, the action that I take is to delete. And again, that reconciliation loop that was doing creation and health checking is now also doing delete. Same logic, same exact code path, same set of small unit tests. All right. And so this concept of reconciliation also comes out in Kubernetes beyond individual pods. It comes out in the notion of a replication controller. So a replication controller is a combination of a template, that's the desired state template that you see up there on the left, some labels. The labels are there to query out into the world to get the current state of the world, and a number. I want 3. So you might say something like, this is the definition of what it means to be a back-end pod. It's running this image, it has these flags, it has this much CPU. That's the template that's up in the upper left there. Then you have, I want these labels to define the set that I'm replicating across. And what that means is I take those labels as my query, I go out to the pods and I say, how many pods match this label set? How many pods match backend and production? And I take that number, that's my current state of the world, and I difference it against the number that I want to have. Maybe I want there to be 3, and there are only 2. So I take an action, which is to create another pod. Maybe there's 4, and I want there to be 3. I take an action, which is to delete another pod. All right. Now, the other aspect of the reconciliation loop that exists is the idea of a service. Now, a service is really, once you start replicating out containers and you've decoupled yourself from machines, so machines no longer have any real meaning. Now, way back in the day, machines had meaning and we gave them names. We called them MySQL, or we called them Database 1, or we called them Frontend 1 or Frontend 2. They had these nice names and they were very easy to find and nothing moved around. It was bad when the machine failed. It was bad when database failed and we tried to nurse it back to health as best we could. But it was very, very easy to find. When we needed a database, we knew where to look. Now, in this decoupling, it's not a free, there's no free lunch here, right? So in the decoupling of our application from our infrastructure, what we have lost is the fact that any particular machine has a particular identity. And so what we have to regain is the ability to discover conceptual things like database, like back-end service, like front-end service, in this world where things are dynamically moving all over the place. So a service is really the concept in Kubernetes that allows you to do this. Services get a known static fixed IP address. They have a DNS entry that's associated with that known static IP address. The IP address itself is actually fake. It doesn't actually exist except for in the routing tables of the machines in the cluster. But it's this sort of port in the storm that allows us to configure a front end so that all it knows is, hey, I'm supposed to talk to this thing called backend. And well, Kubernetes will take care of making sure that all of the things that implement backend are associated with this service. This is really powerful because it means as that implementation of the backend grows or shrinks or dies and is restarted, the front end is completely decoupled from any knowledge of where those things are. In fact, it doesn't need to know where those things are. So this is, we all know at this point, or at least I hope we all know at this point. Actually, I talked to some people and they don't know, it's scary, but that you should put a load balancer on the outside of your service, right? Every service should have a load balancer at the very edge. It's a cloud-provided service or a F5 router or whatever it happens to be. You put a load balancer out there because you know that's the only way to have reliability. What I'm saying here with services is you want a load balancer between every single layer of your application. And that's the way that you achieve this decoupling, not just of your application from its infrastructure, but of your application from the various pieces of your application from one another. And this is really, I think, the core notion behind the microservices sort of buzz and revolution that's been taking over the world lately. It's really this idea that you want to decouple every piece of your application that you want to decouple. And part of it is because it actually facilitates team growth, right? Suddenly, if you decouple and you put an interface, an API interface and a load balancer between these two pieces of your service, suddenly one team, maybe it's even a remote team, can take over that component. You can have another team grow and there's a lot of work out there that says the ideal size of a team is somewhere in the range of 6 to 10. And I can attest to this personally, right? Like above that, it becomes hard to coordinate. And so as your infrastructure grows, you need to have infrastructure that's decoupled in order to facilitate that growth, in order to be able to make sure that the people who work on your back end don't necessarily have to talk to the people who work on your front end very much. And indeed, I worked in search infrastructure on the back ends for Google Search for 4.5 years. And I actually relatively rarely talked to the people who worked on the front end, the web UI that you guys see. In fact, when I did, it usually meant something really tragic had gone wrong. So a service is, again, an example of this reconciliation loop. It has a name that's sort of the conceptual front end, back end, whatever. It has a series of ports, one or more. And again, it has a label query. And the label query, this time, identifies the set of things that implement this service, right? So it gets its static IP address, it gets its DNS name, and then the reconciliation loop is constantly looking out into the world, executing this query, finding the pods that match this query, and so making them the set that the load balancer balances across. And so as pods come and go, health checked or not, resizing or not, this load balancer is constantly reconfigured to point to the right set of applications. All right. So now, having seen all these objects in action, it's time for the demo. I hope I'm doing OK on time. I'm probably OK on time. OK, so I'm living dangerously and running this on the super flaky conference Wi-Fi, which you've all been experiencing, I think, at least I hope. So we shall see how that goes. And if not, I'll whip out my cell phone and we'll go and tether. All right, so localhost. I see. We will hope that the network works. I was actually really proud of myself, and I got it all working on my laptop without any network earlier, and then I broke it. And so I had to have my backup VM out in the cloud, but if the network doesn't work to get up to the cloud, that's going to be a problem. I'm going to have to kill this. Oh, that worked. That's amazing. Okay, I'm on my phone now. This is just payback because Kelsey, did a demo at the Kubernetes workshop a while ago, and we totally failed for him. So I know he's out there. He's messing with the Wi-Fi. He's messing with the Wi-Fi. Yeah, he recovered beautifully, actually. It was amazing. Well, that got farther. Anybody have any questions? Oh, there we go. We're in. Excellent. All right, let's reload here. Hopefully this will work. Just see. Waiting for. All right, that's there. Oh, yes. Always makes me good. Although you really want to see blood, right? Like you actually know. Yeah. I know. I've been out there. All right. So I have here an application, and what we have here on the upper left is the service. It's got that static IP address. We have 3 pods. They're controlled by a replication controller on the right-hand side. So 3 pods running v1 of my application, controlled by the replication controller, service in front of it. Now, if we take a look at what this application actually looks like, it is an awesome application. But it's only awesome application v1. You wouldn't believe the features we have in awesome application v2. And so we're going to go over here, and we're going to do a rolling update of this awesome application v2. I'm going to have an update period of 2 seconds, which means in between downing one and upping another, it's only going to be 2 seconds. Don't do this in real life. But you don't want to sit here and wait the appropriate 3 minutes between each down and up that it would otherwise take. So in the interests of time. So what you see here is I've actually created a second replication controller over there. It's created one instance of application v2. And now it's going to sort of turn the dial down on one and turn the dial up on the other. So let's go take a look at application v2. Wait a minute, it has cowbell? We're supposed to have more awesome. That's not good. That's really not good. All right, so let's kill that out. All right, let's go back. See, this is what happens. OK, well, so we were in the middle of our update, and it didn't really work out for us. Well, what are we left with? Well, we're left with 2 running v1, and we're left with 2 running v2. Let's do some work to restore that. So we're going to go up here, and instead of rolling update my app, we're going to do a resize of my app to, oops. Let's see. Replicas equals 3. So let's resize that back up to 3. OK, so now we have 3 running v1 and 2 running v2. So we basically restored the v1 that we had before. Now let's delete, say, delete RC. And that's going to take down the new thing that we said. And what's important to note here, and they're down, what's important to note is throughout that whole thing, the service was being mapped across all of them. Right? So the load when I had 5, the load balancer was spraying across all of them. And of course, it was sadly displaying my awesome cowbell instead of my awesome app. And that's my fault, essentially, for doing the wrong rollout. But I never had a service interruption. Right? I never had a situation where the world was down, and in 2 minutes, I've restored myself back to v1. Well, now I've fixed whatever that problem was that I had. And now I'm going to actually go back, and I'm going to do a rolling update now to v3. Let's go back out over here. Again, what it's going to do is it's going to create a new replication controller. And that new replication controller is going to create an instance of v3. And now it's going to we have 1 at v3 and 3 at v1. It's going to turn down the knob on v1. And one of the v1s is going to disappear. And now we have 2 at v1 and 1 at v3. And now it's going to turn up the knob on v3. And a second v3 is going to appear. Right? And this is all happening with the replication controllers and the labels, identifying the set of machines that I want to be serving across. And if I take a look at my app over here, of course, now it has more awesome. So that is really, that's what I wanted in the end. And at the end of the day, now I have 3 running v3 and a single one running v1. It's going to kill off that single one running v1. Again, the service is being mapped across all of these all the time, and now I'm down to 3 at v1. And the last stage is essentially to rename that first replication controller to be my app instead of my app with that ugly hash at the end. Now, oftentimes, this is one instance of a pattern where you kind of want to dynamically update the same replication controller. Some people actually want to encode the version in their replication controller. And so you'd go from my app v1 to my app v2 to my app v3. Oftentimes, these configurations are actually checked into source control rather than being an imperative thing that you run on the command line. And the rolling update command that we have in kube control supports that as well. And so I hope, I'm sort of pretty much out of time at this point. I hope that I want to end with questions as well as to say, I hope this showed you that really, if you're looking to simplify your system, decoupling as much of the things as you can from one another both provides scalability for your team as you look to grow, areas for people to focus and develop areas of expertise. The people who know about kernels don't have to be the people who know about Ruby on Rails or JavaScript or anything else like that. And I want you to see how CoreOS, as sort of the people who understand the operating system and how to operating system, and Kubernetes as sort of the cluster operations layer, really allow you to take your application apart into individual pieces that really can be treated independently for more reliable, scalable growth. So thank you very much.